Okay, we are going to start in section 1.6, talking about absolute value functions. So an absolute value function, if we actually think of what the definition of it is, we can express it as a piecewise function, which we've been talking about in previous sections. So we write it, of course, with bars, like these straight lines around some expression in the middle. And there's two cases, right? If the thing inside the bars is positive or non-negative, then it's just the expression inside. And if that expression inside is negative, then it's negative of the expression inside, right? So if inside we had 3, well, that would be this case here. 3 is greater than 0, and the output is just 3. But if inside we had negative 3, well, which case are we in? Negative 3 is less than 0, so it would be negative 3, which would be, again, positive 3. Right? So we could think of absolute value as a piecewise function. And conceptually, let's think about what we're talking about here. So what if we wanted to describe all values x within or including a distance of 4 from the number 5? Okay, so here's number 5, right? And we want to know what all the numbers, we want to describe all the numbers that are within a distance of 4 from that value 5. Well, we could write it like this. X, all the x's such that x minus 5, the absolute value of that distance between our number and 5, is less than or equal to 4. Okay, so conceptually, that's what we're thinking of with absolute value. And it's one of our toolkit functions. You've seen the graph. You know, it's like comes to a point, kind of like a vertex, but not. And for just a regular y equals absolute value of x function, that point is at 0 at the origin. And let's see, these lines go up with a slope of 1 or a negative 1 from that origin. So let's just notice the distance when y is 1, the distance between these two points on the function is 2. And when y is 2, the distance between the two different parts of the function is 4. And when y is 3, the distance is 6. Okay, we're going to use that in a minute. So this is our standard absolute value function. All right, let's think about transforming it. Okay, let's relate this to our last section about transformation of functions. So here in blue, we have our standard absolute value function. Okay, well, if we moved it to the right 3, it's going to look like this. Okay, the red function. We're going to move it to the right by 3. So let's remember back. X minus 3, if that's inside our operator, x minus 3 moves it to the right by 3. Okay, so our new function, our red function, looks like this, the absolute value of x minus 3. And now what if we did a vertical stretch? Okay, if we stretched it up by 2. Okay, our green function here, if we stretched it by 2, we'd have this function here, 2 times x minus 3. And let's just notice, if we did a vertical stretch by 2, let's see, now when the y value is 2, the distance between them, between the two parts of the v, is 2. Do you remember in the last slide, in our standard function, or we could look right here, in our standard function, the blue one, that distance is 4. Right? And now that distance is 2. So by vertically stretching it by 2, that distance has been halved. Okay? Okay, and now, lastly, if we wanted to get to this orange function here, lastly, we shift it up by 4, right? We move that point up by 4, and that would be the equation for our transformed absolute value function. It's been shifted to the right by 3, vertically stretched by 2, and vertically shifted up by 4. Okay, so let's look at this function and try to write an equation for it. Okay, well, definitely looks like it started as an absolute value function, right? And the vertex has been shifted over 3 and down by 2. Okay, so there's going to be a horizontal shift to the right by 3 and a vertical shift down by 2. And it also looks like it's been maybe vertically stretched. And let's see, 2 units up from the point, the distance between the two parts of the V is 2. Okay, well, that's similar to what just happened on the last graph, right? And that was a vertical stretch by 2. So the distance between these two parts of the graph has decreased by a factor of 2. So that's a vertical stretch by 2. So let's just think first, for the vertex, we went over 3 and then down 2, right? That's going to give us this green function here. And now we need to stretch it. So again, we're looking at this ratio, right? So if we go the ratio between how high we are from the vertexy thing, the point of the function, in our original function, that ratio is, we go up by 4, and this distance is 8. So that ratio is 2 to 1. But here, the ratio is only 1 to 1. So that tells us our vertical stretch is 2. Okay, so this is our horizontal shift to the right. This is our vertical shift down. And this here tells us that we have a vertical stretch, a factor of 2. Now, one thing that's interesting to think about is we could also consider this a horizontal compression, right? Like we took our original V and we squeezed it together. We could think of this as we're stretching it up, or we could think of it as we're squeezing it together horizontally, okay? So we could put that 2 inside as a horizontal compression. Algebraically, these two things are equivalent, right? We can put the 2 inside the absolute value or outside the absolute value, and we could think of that as a vertical stretch or a horizontal compression. So it's kind of interesting that those things are equivalent. So in this case, we have a nice ratio that we can look at to figure out what that vertical stretch or horizontal compression might be. But what if we couldn't do that? What if it wasn't, if we were looking at a transformation of a different kind of function and we weren't sure what that vertical stretch would be? Okay, I need to not use my mouse, I guess, so that thing doesn't pop up. So we know that the 3 for the horizontal shift and the 2 for the vertical shift down are pretty straightforward, right? But the question is, what is that A value? What is that vertical stretch out front? Well, if we didn't have a nice ratio to use, this is an algebraic way that we could always solve it. We could find a point on the new graph and plug it in. Just, this should look familiar, like if we were finding for a line like the y-intercept, right? We have one variable we want to solve for. We can choose a point on the function. So in this case, they chose that they chose the point 1, 2. You could choose any point on the new function, and they plugged those values in for x and y into the function, and then could solve for a, which would be a vertical shift value. Okay, so if you know there's a vertical stretch. So if you know there's a vertical stretch, but you're not sure what it is, you can use this method. Okay, you can use, like, say, okay, so the vertical stretch is a, choose a point on the function, plug those values in for x and y, and then solve for your variable. Okay, so that will always work. Yep, okay. So that is sort of an introduction to absolute value functions. We'll continue. Now we'll look at algebraically solving them in the next section.